Okay, I looked up the looked at the Khan Academy videos for this next part of solubility equilibrium, and there was nothing that quite fit. So we're going to do this one together with a short video here. I've got some practice for you to try, and we'll see how this goes. I have got your questions about what about the review sessions. We're going to see obviously this. This distance learning is going to continue after spring break. So can we do something on Zoom? I'm going to look into that over the next week and see what if I can answer some of those and we can set things up. So let's get into this part. It's section 17.6 in your textbook, and it's about precipitation and solubility. If I have a relatively insoluble compound, can I predict in a mixture will a precipitate form? I'm going to mix two different solutions, and see when I mix them, will a precipitate form? So that's what this last topic on solubility equilibrium is about. So here's my problem, and so you can pause the video to copy this down, but I'm going to take 100 milliliters of a 0.0015 molar solution of copper 2 nitrate. I'm choosing copper 2 nitrate because nitrate's always soluble, right? So the copper 2 ion can form precipitates with certain things, but since it's with nitrate, it will be soluble. So this is a completely soluble compound. I'm going to take that, I'm going to add that to 100 milliliters of a 1.5 times 10 to the minus 6 molar solution of sodium carbonate. Also, so carbonate tends to form insoluble compounds. It will form insoluble compounds with a lot of things. So what have I done? I've combined it with sodium. Sodium ions are soluble with everything, right? Alkali metals are one of those things that are always soluble. So this is a completely soluble compound. Here's another completely soluble. But when I mix them, I may form a precipitate depending on how much of the copper ions and the carbonate ions are there. I'm given this also for the problem. The equilibrium constant, or the solubility product constant, for copper 2 carbonate is 2.3 times 10 to the minus 10. I got that from Appendix D. So this is a very insoluble compound, right? 10 to the minus 10. So this thing will form precipitates easily. Do I have enough, though, for me to have a precipitate? That's what this is about. So I'm going to have to erase the problem so you can pause it to copy it, and then I'm going to erase the first part of this problem so I have room to work. Okay, so let's turn that problem into a picture problem. I'm going to take .0 milliliters, milliliter small, and then that's going to be the sodium carbonate, right? And its concentration was 1.5 times 10 to the minus 6 molar. To that, I'm going to add 100.0 milliliters of my copper 2 nitrate solution. And that was a 0.0015 molar solution. So I'm looking at this mixture. Now, there's a lot of spectators in here. The nitrate's a spectator, the sodium's a spectator. So let's kind of draw what we've got. I can put it over here. No, we'll put it right here. In my solution, to determine if there's a precipitate, what am I really looking at? I'm looking at how much copper 2 ions, what is my concentration of copper 2 ions, and the other one is the carbonate. What is my concentration of carbonate ions? Those are the things that would form a precipitate. The others are just spectators. So concentration of copper equals, well, let's see, in my copper 2 nitrate solution, I had 0.0015 molar but that was in 100 milliliters. My total volume of solution has now doubled. So 0.0015 molar was my initial concentration of the solution, but now that I've doubled the volume, the concentration cuts in half. And you get equals 0.3075 molar. I'm going to erase this top part so I can fit. I want to keep this up for now. I can erase this. We don't need this. My concentration of carbonate. It was 1.5 times 10 to the minus 6 molar. I have doubled the volume, so it's half of that, which is 7.5 times 10 to the minus 7 molar. So that's my new concentration. So I've got my concentration in my new mixture of copper ions, and I've got my concentration of carbonate. Now this is an application of what we did just at the beginning of this week with the reaction quotient. So KSP for copper 2 carbonate, let's write the expression. KSP equals the concentration, so I kept this one fairly simple. Sorry, let me write the, before that, what is the reaction? Or if it is an equilibrium of a saturated solution of copper 2 carbonate, I'd have copper 2 ions and carbonate. Oh, I think I'm off the count. Carbonate. So I've got that one. Let's write the equilibrium expression. We'll put that one in. Sorry, let's go here. So the equilibrium expression for this, KSP, equals, since it's just first power, is just that, right? So it's, of course, this is a solid down here. It's not part of the equilibrium expression. I've got copper 2 ions to the first power, carbonate just squeezed off there to the first power. So here is my equilibrium expression. Now what we had with reaction quotient, so this thing at equilibrium is 2.3 times 10 to the minus 10. That's at equilibrium. The reaction quotient, Q, is a test. Am I at equilibrium? And if not, which way will this thing go to get there? It's the exact same expression. Cu2 plus, CO3 2 minus, exactly the same. But what I do is I plug in the concentrations, plug them into this, and see, is it 2.3 times 10 to the minus 10? Is it something different? So let's do that. For copper, I had 0.00075. If I got that right, yes. For carbonate, it was 7.5 times 10 to the minus 7. So I figured out the concentration of each ion. I plugged that in to my equilibrium expression, and I see what that comes out to. I've multiplied that together, and I got 5.6, rounding to 2 sig figs, times 10 to the minus 10. So I found that. So now the question is, will a precipitate form? What I do is I do a little check. If Q is greater than KSP, which it is in this case. KSP was 2.3 times 10 to the minus 10. I get a number here that is greater than that. So I get a number bigger than that. What does that say? That says it's too full. This is too much. These concentrations, this combination of concentrations is too much. My number is too big. The solution can't hold that much. A precipitate will form. So if I get a number that's greater than KSP, these concentrations, that's too much, that's too big a number. It can't hold that. Precipitate forms. So now I get a precipitate that's going to form, and I will get this, so some will come out, right? So because there's just too much, the solution can't hold that much. There might be some where I'll get, if Q, what if the number came out less? And just a smaller number, what is 5.6 times 10 to the minus 12 or something? That means it's not full yet, it could hold more. So if the numbers I put in here are less than the expression for a saturated solution, then it could actually hold more. So if Q is less than KSP, no precipitate. And I've got a little practice for you in part of this in one of the problems of the book. So this is just all we do. Figure out what my concentrations are. So I go through and we found these first. What are my actual concentrations of each ion in the mixture? Plug that into the equilibrium constant expression, and then do this check. Are those concentrations greater than KSP? Then it's too full, a precipitate. Some of those ions have to come out as a precipitate. Is it less than? Then no precipitate will form. I could actually add more before I get to where a solid would form. So that's some of those problems. There's some practice in there. I want to give you one more, just quick, not actually working a whole problem, but an example. And because there's an AP problem I would like, FRQ I'd like for you to look at. What if I had this? 100.0 milliliters of a sodium carbonate solution. And let's just say it was like 1.5 times 10 to the minus 6 molar. And then what I'm going to do is, now it's going to be a little bit more concentrated. I'm going to add Cu and O3 2. I'm going to add a concentrate, right? Or I could even add a little bit of solids, but usually this would be some sort of concentrated solution, dropwise. Drops. I'm going to add a drop at a time. And then we would say, okay, at what point will a precipitate form? Notice my KSP, I'll rewrite it. Equals concentration of carbonate, copper 2. I'm adding copper 2, I already have a known concentration of carbonate. So I would plug that in, right? Since it's 1 carbonate per compound, 1.5 times 10 to the minus 6. And then, so what's my unknown? Copper. How much of this dropwise will I get before I form a precipitate? So that can be my unknown in this way. So we've got some practice on that kind of problem coming up too. I'm just switching the unknown and varying this with that. Okay, there's some practice there, and we're going to just continue our review through spring break and regroup again after spring break. Have a good break.